Welcome to The Explainer. So today we're getting into something that, well, it haunts pretty much every software developer out there. You know the feeling, right? Where some systems just feel like this giant house of cards, just waiting for the slightest breeze to knock it all down. Well, we're going to dig into this really powerful, surprisingly old idea that gives us the answer.
Oh man, we have all been there. You make this change you think is super tiny, totally insignificant, right? Just one little tweak in one corner of the system, and then boom, everything, and I mean everything, just breaks. It's this insane cascade of failure, and you're just sitting there thinking, how did that cause this? But why does that even happen?
Well, it turns out the answer has been sitting there for a long, long time. We're talking about a foundational paper from way back in 1972 by a computer scientist named David Parnas. It's a total classic, and for a good reason. It was written to solve this exact frustrating problem.
So Parnas was really wrestling with this core engineering concept, modularity. And the dream of modularity is, it's pretty simple. It's the idea that you can take a massive, super complex problem and just break it down. You chop it up into these smaller, independent, much more manageable pieces. We call them modules.
And listen, if you get modularity right, the payoff is just huge. Parnas points out three massive benefits. First, you get faster development because different teams can work on their own little pieces at the same time. Second, you get flexibility. You can actually change one part without, setting the whole thing on fire. And third, it's just plain easier to understand. You can look at the system one piece at a time. But here's the million-dollar question. It's not if we should do this, it's how. How do we actually decide where to draw the lines between these modules?
Okay, so let's start with what feels like the most obvious approach, the one most of us would probably come up with first. Parnas has this great name for it. He calls it the flowchart trap.
To make his point, Parnas uses this really simple example system. It's called a keyword in context index, or KWIC for short. So imagine you have a line of text, like the quick brown fox. The system creates what's called a circular shift, so you get quick brown fox the, and then brown fox the quick, and you keep going. It does that for every single line you feed it, and then it just sorts that giant list alphabetically. Pretty straightforward, right?
So here's a question for you. Just take a second and think about it. If you were the one building this, how would you slice it up into modules? What feels like the most natural, logical way to divide this process?
If you're like most people, you probably landed on something that looks a lot like this. You'd break it down based on the sequence of events, the flow. So you'd have an input module, then a circular shift module, then an alphabetizer, and finally an output module. It makes perfect sense. It follows the data, and it just feels right.
And look, this approach is clean, it's intuitive, it's exactly how you'd sketch it out on a whiteboard. But, and this is a big but, hiding just underneath this simple logic is a massive flaw. A flaw that makes the whole system incredibly fragile. And this is where Parnas just completely changes the game. He basically argues that we've been asking the totally wrong question all along, and that the real key to a strong design lies in a completely different way of thinking.
He just flips the script. Listen to this quote directly from the paper. We propose instead that one begins with a list of difficult design decisions. Each module is then designed to hide such a decision from the others. So get this, he's saying don't start with the process, with the flow. Start by listing the things that are hard, the decisions you're not sure about, the things that are most likely to change. And then you build each module specifically to hide one of those decisions from the rest of the system.
And that right there, that's the core of what he called information hiding. The idea is that a module's number one job is to protect a secret, a specific design decision from everything else. The other modules, they don't need to know how the secret works. In fact, they shouldn't know.
This table just nails the shift in thinking. The old way, the flowchart method, it's all about the processing flow. It's always asking, okay, what does the system do next? But Parnas's idea, information hiding, is totally different. It's based on hiding those tough design choices. It asks a much, much more powerful question. What part of this system is most likely to change? And that simple change in perspective, well, it's everything.
All right, so we've got two competing ideas on the table. We have the intuitive flowchart method versus this new information hiding method. It's time for a showdown. Let's put them both to the test and see which one actually holds up when things get messy.
I mean, this is the ultimate test for any design, isn't it? It's not really about how well it works on day one. It's about how well it can adapt when things inevitably change down the road. So which of these methods gives us a system that's resilient instead of brittle?
So in the paper, Parnas lays out this simple but really insightful stress test.
The original design just assumes that all the lines of text can be stored right there in the computer's main memory. But what if the system gets popular? What if our dataset gets way too big for that? We can no longer hold everything in memory. We have to fundamentally change how we store and access all that data.
Okay, so what happens to our flowchart design? Well, it's a complete catastrophe. An absolute disaster. Because every single module was built with the assumption that it could just reach into memory and grab whatever data it wanted. They all have to be changed. The input module, the shifter, the alphabetizer, the output, every single one breaks. One single design change forces a total rewrite of the entire system.
Now let's look at the information hiding approach. The result could not be more different. Here we had a specific module, line storage, whose entire job, its whole reason for being, was to hide the secret of how data was stored. So it's the only module that needs to change. The other modules? They never knew the secret in the first place, so they don't care. They are completely unaffected. The change is perfectly, beautifully contained.
The results of this little thought experiment are just so clear you can't argue with them. And they point to this timeless principle of software design that is honestly probably more important today than it was even back in 1972.
So here's the punchline, the single most crucial point. We need to decompose our systems not based on the steps in a process, but based on the design decisions that are most likely to change. The best modules are the ones we build around our biggest uncertainties.
And Parnas even gives us a handy list of the kinds of secrets we should be looking to hide. Things like the specific data structures you're using, the format of low-level control blocks in an OS, character codes, data representations, even the exact sequence that you process items in. Every single one of these is a potential weak spot that you can make stronger just by hiding it away inside its own module.
And let me be clear, this idea of information hiding isn't just some dusty old concept from a textbook. It is the absolute bedrock of modern software engineering. It's the core idea behind object-oriented programming. It's what makes for good APIs. It's the entire philosophy behind microservices. All of these modern practices are really about one thing: hiding implementation details to build systems that don't shatter the first time you touch them. So that brings us to the final, really important question that we should all be asking ourselves in our own work. When we sit down to design something new, we need to stop just asking what are the steps and start asking a much better question. What are our secrets? What are the design decisions we're making today that we are most likely to regret later? The answers to that question, well, that's what will guide us toward building software that actually lasts.